is what has been discussed there. I'll come to that. Okay, I'll come to that. So now just let me open my iPad. Okay, so I presume that you're able to see my screen, right?
Yes, sir.
Okay. See, I'll just give you a non, what do you call, mathematical. I'll skip all the places where in which there are, what do you call, detailed mathematics involved. I'll just give you a brief recap. So now you have the data. Okay, now that is fine. Now, the idea of latent variable model is now, okay. So now you want to come up with a Z. Okay. So now when you go ahead and perform the marginalization, you should be able to get the value of the data distribution. Okay, so now here, now the idea is, so for every x that you have, so there is a latent unobserved variable. Okay, so now the idea is, if I catch hold of that z, okay, now from z I'll be able to go to x, is the idea. Okay, that is the basic idea. So now what are the ways in which I can catch hold of z is the question. Okay, so now, yeah, now for each xi belongs to d, we assume that there exists zi corresponding to each xi. Okay, so now you have zi, now that is corresponding to xi. So now the question is, now, okay, now if I'm able to sample from zi, if I somehow am able to sample from zi, okay, so now that means that I'll be able to obtain new examples of xi. Okay, so now that is the idea. So now the first of that, yeah. So now you start with getting the elbow. So I presume that you are quite comfortable with the idea of elbow. This comes again and again and again. So now even in diffusion models, yeah, you will be dealing with the same elbow. No, but yeah, no, there, since you have a lot of latent uh, spaces, so now it will be much different, but the idea remains the same. So this elbow is not some random thing that we have got. Now this is a pretty interesting idea. So, and then we looked at the example of Gaussian mixture model. See, the idea is, now your data is not combination of one, so it has multiple Gaussians like this. Okay, so now in that case, if your data is like this, now how do you sample? Now this has alpha 1, alpha 2, alpha 3. Now this is now the probability that you choose from these Gaussians. So, and then if you add alpha 1 plus alpha 2 plus alpha 3, now you should be able to get 1. So, and then you proceed. Okay, yeah, that is the idea. Here, see, p theta of x is that you choose, now what is the probability of choosing that specific Gaussian. Okay, like that, if you have m, so you add them. Okay, so now yeah, so I will not be going ahead with the EM algorithm. So I prefer to go to directly to latent variable models, now which is variation autoencoders, now VAE. So yes, so you get to know this, so you get the elbow. So now what is the idea? So now the idea is, now learn a latent variable model with unknown, now p theta of z given x. So now I'll give you an x. Now you should be able to obtain the z. Now then I'll be using that z, enable sampling from p theta of x given z. I'll use that z so that I can get values from this x. Okay, so now, and then again enable posterior inference. Now that means that given x, so now I should be able to find the probability of z. Okay, so now how do I, this is the idea. So now for every x, now you should be able to find the latent, and using that latent, you should be able to sample it back. Okay. This is the underlying idea that is there. Okay. So now then how do you do it? This is one approach, which is a deterministic approach. So now what do you do is now you give z, now you will be able to obtain x hat. Now this is similar to that of a GAN operator, and then you have a classifier. This we have seen. But the idea of probabilistic approach is now you give x. Now I'll not be giving you z. I'll be giving you parameters of this distribution. Okay, I'll be giving you the parameters of the distribution. Now use those parameters and sample from the distribution. Pass that sample through the through this neural network to get the parameters of x given z. Since you have got the parameter, no sampling, no using those parameters and sampling no, would not be a difficulty. Okay. You give the x. So now you go to this, you pass through this neural network, and then you get the parameters of q phi. Okay. And using those parameters, you sample. And using those samples or some modification of that sample, pass through the decoder network, and then obtain the parameters of p theta of x given z. Okay. So now and then, okay, now try to get a new data point. Okay, and you can see that there is no link direct, there is no link between the encoder part and then the decoder part. Now the encoder will give you the output of q phi, and then the decoder will give you the parameters of p theta x given z. Okay, yeah, and then we looked at the idea of reparameterization. No, I prefer not to go ahead with that. So now finally, now you should be able to understand now what is that. Now finally, we use the reparameterization trick. So and then now we do that. Now given an xi, now I will come up with mu I and sigma I. Now, preferably this sigma I will be a diagonal covariance matrix. So I just need to get the diagonal elements. Okay. So now that means that if your z dimension is the dimension z belongs to Rk, so now this will be k dimension, this will be k dimension. Now it should be k cross k, but as I'm telling you that, now I only need the diagonal elements, so it will be possible. Then you sample. Okay. You sample from this distribution. Now how do you sample from this? You have got the parameters. Okay, fine. Now you can sample from normal distribution, and then you can reparameterize. So, and then you pass it through the decoder network and then get the parameters of p theta. Okay, so this is the idea. So yeah, so and then it finally reduces to the idea of reconstructions. So yeah, as I told you, this is d dimension. You convert it into k dimension, and then you get parameters of. Now, how does the forward pass happens in this case? Now, given an x, now pass through the encoder and obtain this. Okay, now sample m things, m noises outside the neural network using the standard Gaussian. Now, once you have them, calculate m zis, so m such zis, and then what do? You pass all of them through the decoder. Now, what will happen? Now, you get m such elements. Now, for each of those elements, yeah, you come up with the MSE loss. Now, how does the backward pass happens? Now, you have to find this with phi. Now, this is phi, this is theta. Now, how do you do it? Now, back propagation through. Now, you keep theta as constant. Okay, and reparameterization is independent of p. So, it is just like phi of this, p theta of. Using this, now I'll be able to backprop. This is the second term. Now, this is a straightforward computation. So I'll not be going ahead with that. Now, this is training the encoder. Now, how do you train the decoder? Now, how do you get the parameter theta? Now, you perform a forward pass same as the encoder. Okay. In the reverse path, now once the decoder is in, you will just stop it. Now you will not pass the gradient through the encoder. Okay. That is how you obtain the training process. And how do you infer? See, the idea of inference is very simple. Now you obtain new ZI and then pass it through this. Okay, you get this. This is the mean. Now either you can consider this itself, the mean itself, as a data point, or what you can do. Okay, now if you don't want to consider this itself as a data point, okay, now you take multiple of them and then you take the average of it and give it. That is also a possible way. Now, post your training, now your inference is only through the decoder. Okay. This is the idea of the encoder decoder model. Okay. Yeah. So now then what happens is in naive VAE, now there is an issue of posterior collapse. Okay. Now the idea is, now the decoder will see it difficult to differentiate between two samples, xi and xj. Now why is that? Now your q phi of z given xi and q phi of z given xj, both of them is the same distribution. Okay. So now this is an issue. Now this issue is what is called as a posterior collapse. And how do you avoid this? Now to avoid that, you should add a regularization. So if we have a regularization term, we want to give a more weight to it. Now that give rise to the idea of beta VA. You just add a beta factor here. So and then now you have more weightage for this KL term, because of which the issue of posterior collapse now will be avoided. And then comes the vector quantized VAE. Now in vector quantized VAE, the idea is that the latent space that you have is discrete. Okay. So and then so the thing that is that you have a learnable dictionary. Okay. So now that you have dictionary L, now wherein which you have Z1, Z2 till Zm, each of them is of dimension K. Shashi, does that answer your question?
Yes, sir. So once more, can you clarify what the rows and columns mean, like of this K cross D tensor?
Okay. See, the tensor is like, now what is K? Now K is rows. Okay. This is okay. Now you have P columns. Okay. Now why is this P there? It has to be M, is what I feel. Wait a minute. Yes. It has to be M. Okay. Now you have Z1, Z2, so until Zm. Okay. This is your dictionary. Okay. Now whenever you get a Zj, now you want such an vector from this dictionary, now which has the least distance from that. This is what is called as vector quantization. Okay. Does that answer your question, Shashi?
Yes, sir.
In practice, we will have blah blah blah. Okay. Now the training procedure is like, yeah, you have this reconstruction term. Okay. Now this is your input. Now this is your vector quantized latent, and then from which you have got the reconstruction, and then the MSE, or the second norm between the encoded data and then the nearest one which is there. Okay.
This is just a column from that L dictionary,
Yes,
right?
it is just a column from that, correct, which has the nearest distance.
Yes, sir. That is understood.
Okay. And How does the inference happen? Now, one is now you can get the embedding. Now, how do you get the embedding? Now, you pass the X test that will give you ZE. Now, the one which is having the least distance to this, whatever you have got, is the embedding. Now, this is the posterior inference. Now, how do you sample from that? Now, you sample from the dictionary. So, you will be able to get it. To be able to sample from the decoder of the V, we need to sample from the distribution of this. We need to be able to sample from this, the distribution of uh, the dictionary. Okay. So now you have to learn the distribution of that. Okay. So now to learn how to sample from this distribution. Now again, now you have to sample from this distribution. How do you do it? Now you fit a GMM to it. Okay. Now you obtain you pass all the data points. Now once through the encoder. Now that will give you a lot of uh, things. Okay. Now for each of them, now you will be able to get Z, and then you will be able to obtain, let's say that you have 5,000 examples, you have 5,000 Z's, using which you can fit a GMM. And then once you have fit a GMM, so now then you can sample from the distribution. Okay. That is how you will do it. This is the idea of VQVAE. Okay. So any questions here?
No, sir.
Yeah. This is a small recap of whatever has been discussed in week 5 and week 6, which is VAEs, variational autoencoders. Any questions? Okay then. Okay. So all the very best. Now exciting things are coming. So keep yourself ready. Okay. You have a lot more nice things to come. Yeah. Any other questions, guys?
No, sir.
Good. Okay then. So we will wind up the session then.
Sir, I have just a quick doubt.
Go ahead.
So
Go ahead.
it's regarding this DDPM generation in DDPM. So with
Okay.
respect to generation in DDPM,
Mm,
sir says we have to travel T steps to do that generation.
mm.
So because we need to get x the params of xt is given, so from that we have to travel in the reverse, right? So at each step we'll get either what do we get at each step? We get the parameters of each step, or that the xt minus 1 at t.
No, no, no. You'll get the points itself. You'll not get the parameters.
Okay, so okay, that goes inside the equation, so then
Yes.
only we'll get the next value, so that goes into the next one. Okay, sir.
Yes.
By the way, what do you mean by points, sir? Can you expand on
What do you mean by?
that point? What do we get at that each step? What do we get as the output of the decoder?
No, no, no. What do I mean by point is no. It is the no. It is not the parameter. It is the data itself. Is what I meant. Okay. So I use the word point. That's all.
Okay, the noisy data xt minus 1. So,
Yes. You
okay,
get the data point itself.
okay, sir.
So you're done with DDPMs.
I have just gone through the videos, but couldn't understand yet, sir. So I have to. I think I have to go through lectures once again. So.
Good, good. See, it is an extension of VAs. In VAs, you had one step to convert. Okay, now don't look at the idea of sampling there. Okay, you just had one step to go into the latent, but here you have multiple steps to convert it into the latent. Okay, now that is the crux idea. Okay. Sure.
Yes, sir. Thank you, sir. I'll just go through the videos. We'll
Yeah,
make
yeah, sure,
next
sure, sure. By
questions.
the next week when you come, so yeah, you should be comfortable.
Yes. Thank you.
Thank you, sir.
Thank you, guys. Bye bye. Have a nice week.
Thank you, sir. You too, sir.
Thank you. Bye bye. Yeah, Nitin.
Yeah, Chandan, hi. Yeah, closing it.
Thank you.
Okay, thanks.
Hey, I'm extremely sorry for delay this time.